To go. All right, so first of all, thank you everyone who's joining us today, both in person and online. We have at the very least both the brother and the mother of the candidate who is presenting today. Hussein, and we're also very thankful to have Hussein's thesis committee here, who is Arvind, Elena, and Eric, three phenomenal thesis committee members who I'm sure Hussein will talk about later, but have really helped guide his thesis. My name is David Sontag. I am a professor in computer science, affiliated with IDSS as well, and Hussein's PhD advisor. Hussein came to MIT into the IDSS PhD program from Lebanon, where he did his undergrad. He had a stint here in the United States as an intern at the Toyota Technology Institute in Chicago, where he began his real foray into machine learning research. He arrived at MIT in fall of 2019. Some of you might remember that academic year. He started working with me first in a very informal capacity in that fall. January 2020 came around and started, in that very informal capacity resulted in an ICML paper that ended up getting published. And I told Hussein, yeah, you can join my lab. 2 months later, of course, the COVID-19 pandemic began, and we all went virtual for a subsequent long period of time. So it was quite a tumultuous period that I think marks Hussein's thesis. And to remember that, I had to actually go back to my notes to go back to what we had been speaking about 2019 and 2020, because from a research output and from just sort of the collaborative nature and friendship that we've built, it's as if the pandemic had never existed to me. Hussein was able to continue his work throughout and really create and grow very strong relationships, both with, of course, his lab mates, but also very many others in the community. We're very thankful also for many of his collaborators who've joined us virtually in addition to in person. And there's a very, very long list of people who he's worked with on the papers that make up his thesis. So Hussein came in and started talking about how one can think about human AI collaboration. Of course, you'll hear more about that today. It caught my interest because I really care deeply about healthcare. And in healthcare, when one thinks about bringing AI into the running, it's very seldom that AI could be used in absence. Usually it's AI guiding the work of a clinician. And so that notion of how do we develop AI to work really closely in concert with a clinician just seemed to be a core question that we had to develop as a research community. And Hussein's timing couldn't have been better, of course, because that research question has now become a everyday, every minute scenario for all of us in today's world of large language models, Copilot, and so on. And Hussein's research, I think, really sets some of the foundations for the community for how one can think about pushing the mathematical and applied foundations of human AI collaboration over the next couple of decades. So Hussein, we're looking forward to your defense presentation, and thanks again to his committee for being here with us.
Thanks. All right, thank you so much, David, and thank you everyone for coming in person, and thank you to everyone on Zoom as well. Today, I'm going to be talking about human AI collaboration. So I believe in the near future, almost all the decisions we're going to make are either going to be assisted by an AI model or even performed by an AI model. And that's already starting to happen in a lot of applications we care about. So for instance, radiologists are using AI models to help with breast cancer detection and other radiology tasks. Large language models are really changing the way we write code with products like GitHub Copilot and more. And this is really a fundamental change in how humans perform their work. And my goal in this thesis today is going to try to increase the benefit of AI to these people. And the approach we're going to take throughout this talk today is to model the human and AI as a single team, as a single entity, and optimize for its performance to achieve better gains. And this is really motivated by a fundamental mismatch in how AI is trained versus how AI is being deployed. So if I try to measure on this line the performance of the human AI team, currently, approximately we're almost halfway to what a human AI team can accomplish. And this is because AI models are really trained, integrated into these interfaces without considering there's a human actually using them. And we can bridge this gap by considering the human AI team as an entity and optimizing for its performance. So concretely, we're gonna draw things out. So we have the human doing their work on their computer. We build an AI model that can mimic the human performing their task. We take this AI model, generate suggestions from it, and integrate them into the user's interface. All of these two entities together comprise what we call the human AI team. So we have the human part, the AI part, and the interface in which they communicate them. And these present three opportunities for us to optimize the performance of the team. So first, we're going to start by thinking how we can optimize the interface in which the AI presents its suggestions. And we're going to see a design intervention to adapt this interface based on human feedback. The second opportunity is to optimize and train the human themselves. Train them to better be receptive to AI advice and know when and when not to rely on the AI suggestion. The third opportunity is going to lie by changing the training objective of the AI model. Instead of building a model that mimics human behavior, we're going to build a model that complements human expertise. So those are the three opportunities and the three parts of my talk today. So this is the outline for this talk. And each of these three parts are going to be based on published papers in machine learning and human-computer interaction conferences. So let's start with the first part, adapting interfaces from human feedback. The recipe we're going to follow for almost the three parts is going to go as follows. First, we're going to try to create a model of the interaction, a model of how the human and the AI interact. And we're going to follow three steps to create that model. First, we're going to try to think of what are the activities that the human and the AI perform as part of this team. So we have human verifying AI suggestions, AI generating these suggestions, and more rich types of interactions we'll see. So the first step is to list and categorize those. The second step is going to be to figure out the order and transitions between all of these different activities so we can come up with a comprehensive model. Once we have these two steps, the third step is to profit out of this, what we've built. So now we're going to take this procedure and instantiate it with one popular form of human-AI interaction, which is going to be AI-assisted programming. So specifically, we're going to consider GitHub Copilot. So Copilot is a large language model integrated into your code editor interface. And at each moment of time where you pause your writing, Copilot is going to show you in gray a completion. And this completion is not just a single line or word level completion, but can compromise entire functions and classes. And the programmer can accept this completion into their code by pressing tab or rejecting it. And this is really a product that's being used by millions of programmers on a daily basis. And the burning question is Copilot useful to these programmers? We're now starting to have a wealth of evidence for this assumption, some more positive than others. So from the Copilot team, they ran a randomized trial where half the participants had Copilot, the other half did not have Copilot, and they saw a 50% increase in programming speed. Elena and her group had, yeah, go ahead.
Should we hold our questions to the end?
Yes, maybe a clarify. You want to go for your question? Because you're cited here.
No, I guess my follow-up question, because I'm familiar with that work. I haven't reread it very recently. My understanding from that work was that some people were accelerated and some people got slower. They didn't even finish because they ended up having debug code that was recommended to them that they hadn't written. So this I feel like this misrepresents that work just a little bit.
Your
Yes,
work?
some people did get faster.
The first one. The first one?
Oh,
your work. Okay.
Yes.
Yes.
10% faster, maybe an aggregate.
Yeah. So
But
yeah.
some people got
Correct.
faster, some people got slower.
Correct. So it's not a constant effect across people. And when I wanted to say that this was a more negative result than the others.
It doesn't look
Yeah,
negative
yeah.
this way.
Okay,
Yes, I get
perfect.
it.
Let's continue. So that's some initial evidence affirming and negating this proposition. And what could be interesting is how far can we go in improving the performance of this team by just building better AI models. So that's the proposition today. Let's build better models and we expect the performance of this human AI team to increase. So I ran a study where we took the LLM in Copilot and swapped it out with models of increasing capabilities as measured by standard benchmarks. So we had an initial model who was 34% accurate, and we saw humans are 7.5 faster. So this is not a significant effect, but let's move on. So we built another model. We have another model that's 49% accurate, and we expect to see increase in human performance. So now the human is 19% faster. We took an even better model that's 80% accurate on these benchmarks. And what you observe that the human is still not improving in performance. It's still 19% faster. So even though this model is twice as good as measured by standard benchmarks, we're not seeing the effect in terms of human performance at increasing. And so clearly, you could go and build better models, but you're going to reach a point where you're going to stagnate. And you have to try to improve the interaction from a different perspective, which is what we're going to try to explore. So now the question, how can we improve Copilot? So we're going to go back to my proposition. We're going to build a model of the interaction between the human and Copilot, identify inefficiencies, and then try to remedy them. So to understand better how programmers are writing code with Copilot, I'm going to show you on the left a video recording of me writing code, and on the right, I'm going to track the activities I'm undertaking while writing code. So I'm going to begin by writing code for a logistic regression function. So I'm going to write out the function signature. So I'm in this purple state writing new code. And then the Copilot is going to interrupt me and show me a suggestion. But at this point, I'm not thinking about the suggestion. I'm thinking of what is the function signature I want to write. So I transition into the state of thinking of code I want to write. And I immediately reject the suggestion. I continue writing code until I finish my function signature. And now at this state, I expect Copilot to show me something good. And instead, it shows me an empty suggestion in essence. And so I verify the suggestion, it's clearly not good, and I reject it. And instead, what I do, I write my own prompt. So I go into this purple state that's prompt crafting. I tell the model explicitly what I want to do. And so I want to initialize my weight and biases parameters, and it gives me a better suggestion. And now I go into this loop of waiting for suggestions, accepting, verifying, accepting them, and etc. Until I get to another point where I have to prompt craft and then verify another suggestion. At the end, Copilot is going to show me this larger suggestion in gray, and this is the body of the optimization loop. And it's clearly too hard for me to verify initially. So what I'm going to do is I'm going to accept it and then post hoc verify it. So after I've accepted it, you can see my cursor going through it line by line, selecting portions of it that I don't like, and then editing it. And so what this qualitative video is showing you is the different insights we already have gotten. So first of all, the act of accepting or rejecting a suggestion is not really indicative of my preference about the suggestion, but it could be a function of my state when I was writing the code. And second, you can see the wealth of different activities that you're performing, from verifying to prompt crafting, that hide the amount of time that Copilot is adding to the interaction. So to formalize all these insights, we came up with a taxonomy, which we call Copilot user programming states, CUPS for short. And it includes these wealth of activities that I already showed you and more. So these are a set of 12 unique but latent states. So they cannot be observed by just watching the person. You have to ask them what state you were in. And they comprise things like verifying suggestions, prompt crafting, and my favorite state, not thinking. And so to collect data about these states, we ran a study where programmers completed a set of programming tasks. After they completed these tasks, we had recorded a video session of them writing the code. And then with the video labeling tool, themselves annotated their video with the states they were in while they were programming. So now at each moment in the interaction, you have an according cup state, exactly like I showed you in the qualitative video, but at a more larger scale. And so insights from this study comprise these transitions between states. And possibly one of the most interesting things is, where do programmers spend their time when they're writing the code? So on this graph, I'm showing you for each of the 12 cup states. And in light green, I'm highlighting those that are Copilot specific interaction states, like verifying, adding suggestions. The percentage of the session that is spent in each of these states. And we can see that the most dominant activity here is verifying suggestions. So 22% of time is just spent verifying these Copilot suggestions. If you sum up the time, all of these light green states almost comprise 50% of coding time. And these insights also are applied individually to participants as well as on aggregate. So verifying suggestions is really the most dominant activity across the 21 programmers we've observed. So 22% of your time is verifying suggestions. When we look at the fraction of suggestions that were accepted, we only observe that 20% of them were accepted. So if you do this back of the hand envelope math, you could say at most 22% of your time in verifying suggestions is going into all of the suggestions that were rejected, which is almost 80% of them. And if you multiply these two numbers, you can say at most, 70% of coding time is going to waste. And I'm saying at most because you could reject the suggestion, but still benefit from it. So this is really an upper bound on this number. So now the question is, how can we reduce this waste of all of these suggestions that programmers clearly did not want to integrate into their code? And well, the main design thing in Copilot is, when do you interrupt the user? Essentially, Copilot is this large language model and a mechanism to interrupt the user while they were coding. So let's consider two extremes of how we can design Copilot. One extreme is, at every 100 milliseconds, I'm going to show you a suggestion. And it's going to come up with this type of interaction where you're constantly bombarding and you really cannot write any code. So that's not very fun. The other extreme is to only hold out suggestions when you're absolutely certain the programmer is going to want these suggestions. So here, the Copilot is going to wait for me to write my function signature. After I'm done and I've waited for a bit, it's going to show me a suggestion that's going to be more likely for me to accept it. And we can unite these two extremes with the following design. So we build a model that predicts the likelihood that the user would accept a suggestion, given the context that they're in, which includes the code they've written so far and their previous actions, as well as the suggestion itself. And we threshold that probability with a constant tau. And so that extreme where we're constantly interrupting is basically equivalent to a tau equal to 0. So no matter whether it's like that the program will accept, I'm just going to interrupt you at every interval I can. The other extreme is going to correspond to a tau more close to 1, where you're only going to withhold suggestions when you're absolutely certain the program is going to accept them. And so now, how do we design such a system? So we're going to have to build a machine learning model that, given the context and the suggestion, predicts this likelihood. This is a bit wasteful because I have to generate the suggestion and then disregard it most of the time. And so this is really leading to wasteful generations that never get shown. And so another idea is, can we predict this likelihood without even generating the suggestion? So what we're going to do is we're going to decompose this design into two parts. First, we're going to decide whether to even generate the suggestion or not. So we're going to build a predictive model that, given the context, predicts the likelihood of acceptance. And we're going to threshold that to a threshold tau 1. If the likelihood is above tau 1, we generate the suggestion. Once we generate it, we feed it into another model that now takes into account the suggestion and then threshold it to a different threshold tau 2. And we have to design these two and learn these two threshold tau 1, tau 2 to accomplish our initial goal to only threshold with probability tau. And so specific features and the data we fed into this model are as follows. So we gathered data from a 2-week period from almost 500 Microsoft users writing code in Python. So this is almost compromises 200,000 suggestions. And so each suggestion has the prompt that led to it, as well as the previous user actions. And we're going to extract the following features. So in red are features about the suggestion. So they compromise things like the embedding, presence of certain keywords, the model likelihood on that suggestion. And in blue, we're showing features about the prompt, which is basically what got fed into the large language model to generate the suggestion. Again, embeddings, number of tokens, and etc. And finally, in green are session features. Basically, what were the previous actions of the program? Did they just accept or reject the last suggestions we showed them? We can concatenate all of these features and feed them into an XGBoost model that's trained on this binary signal of accept or reject. So now that we've trained this model, I'm going to show you a specific retrospective evaluation we performed. So on this graph, I'm showing you as I vary the threshold tau, the fraction of suggestions I hide, and what's my accuracy when I'm hiding these suggestions. So essentially the true negative rate. So if I hide all of the suggestions, so I set tau close to 1, I'm hiding most suggestions, but I'm making a lot of mistakes because there are some suggestions that program would have accepted if I had shown them. So my accuracy is about 78%. As I am become more selective about which suggestions I hide, I can make sure that everything I've hidden ends up being rejected. And so by clever design of the threshold, you can accomplish whatever trade-off you want. So, one specific point on this curve says that you can hide 30% of suggestions that were shown and guarantee that 95% of them would have ended up being rejected. Copilot implemented a version of this with a very high threshold parameter tau. It only eliminated 4.5% of suggestions and guaranteed that most of them would have gotten rejected.
Sam, what are the small dots?
Bad PowerPoint from me. All right, so this kind of gives evidence that we can try to reduce all of these unwanted suggestions. But maybe a question we haven't answered so far is when do programmers decide to accept these suggestions? But first, let's summarize the takeaways of this first part, which is by understanding the interaction by building this taxonomy, we can understand what are the inefficiencies, and by leveraging the feedback data, we can try to remedy those inefficiencies. So the question is, how do users even know when to accept or reject the suggestion? So we can build a predictive model of this, but what's going on when the user is making that choice? So now we're going to transition into the second part of it. So let's take this example. So suppose you wanted to write code in Lisp. So Lisp, if you all don't know, is one of the original AI programming languages. And if you're as old as David, maybe you've written code. If I give you this code, it's really hard to know what it's doing. If someone already can figure it out, go ahead and tell me. And so if you did know Lisp, you could just read it, verify it, and figure out if this code is correct or not. If you didn't know this, and I told you an AI model generated this suggestion, then you basically decide whether to trust the solution based on whether you think this AI is good or not at Lisp. So based on your mental model of the AI's capability. And in reality, it's going to be a mix of those two things, a mix of verification and relying on your mental model. Let's take another example that maybe more of the audience can relate to. So here I'm going to show you a picture and you're going to ask you, is there a traffic light? And the AI is going to tell you, okay, I see a traffic light, it's there, and I'm confident with 90%. So that's pretty obvious. You can verify it on your own. Now I'm going to make this picture blurry. And the AI, again, is telling me there's a traffic light, and I'm confident with 90% probability. And basically here you're unsure. Maybe you'd guess yes, maybe you'd guess no, but really you're not certain what the correct decision is. Now, what if I had told you that the AI model is often wrong when the car in front has red bright taillights? Then what would you think about the AI suggestion? Probably you'd say, since this image has a bright, the car in front has bright red taillights, probably the model is going to get confused. And so you would say, maybe the model is wrong. And if I blur it for you, you can see this is just a random hood of the car itself, and it's not really a traffic light. And so really having the right mental model of the AI, understanding where it makes mistake, is really crucial to enabling you to perform well with the model. What would the world look like where you had the right mental model of the AI? So if I draw this graph where I'm showing on the y-axis the accuracy of the human, suppose it's at this level, and this is a graph I'm adapting from Christoph Gaius. Suppose I built an AI that's even better than the human. If I put the human and the AI together and the human has the right mental model, you'd expect that the human AI team is even performing better than either. But that's not often the case that we see in practice. The performance of this team is often less than the maximum of the human or the AI. And this is really due to the human not understanding correctly when to rely or not rely on the model. And so in this part of the talk, we're going to try to think, how can we flip this inequality? How can we ensure that the team is performing at least as good as the maximum of the AI or the human? And what we're going to do to enable this is exactly what I showed on the last slide. I'm going to try to describe to you in natural language when you should not rely on the model. So I'm going to try to create these rules that give you a set of guidelines for how you should interact with the model. So here, these rules would be, ignore the AI when the car has red taillights, and etc. And these rules should be adapted to you and your behavior. If you're someone who has the perfect mental model or has a different mental model, the rules I should give to you should be different. Or if you have different eyesight from the other person, also these rules should be different. So to create these rules, first we're going to have a model of the human AI team. And here, the explicit model we're going to do is modeling the decision of the human to rely or not to rely on the AI's advice. And we're going to formalize this by the notion of the integrator. So the integrator is basically the human's decision to either ignore or use the AI's answer, and takes in as input X, the input image as the example, and A, which is the AI's advice. Given these two inputs, we're going to assume the human is making this choice of either ignoring the AI and then trying to solve the task on their own, or using the AI answer and then solving it. Clearly, this is simplification. Often there's collaboration that's happening, but for our sake here, we're just going to stick with the simpler model. And so our first step is understanding this model. So we're going to learn this human's prior integrator from data that we've collected of the human playing this game of predicting these traffic lights. And so here I'm showing you the space of our data. So we have one axis X and one other axis A. And all of this region is basically saying the human is using the AI's answer, except for the small red region where they're ignoring the AI. So now that I have what the human mental model is, I need to figure out whether it's correct or not. So what I'm going to do is I'm going to have a set of data that are represented by these axes. So these are my observations that I've collected. And for each of these observations, I have the human's prediction, I have the AI's prediction, and I have a way to measure which of these two things is better than the other. If the AI is predicting on their own or the human's predicting on their own, which one of these decisions is better. And I'm going to label each of these points by the optimal action the human should have undertaken. And so now you can observe that there's two regions of this space where the human is making the wrong decision. So everything that's a 1 should be colored in blue, and everything that's a 0 should be covered in red. And visually we can see that there are these two regions where the human is making the wrong decision. And we have to kind of explain to the human that these two regions of space, you should in fact make the opposite decision of ignoring the AI model. So we're going to have an algorithm that's automatically going to discover these regions of space where the human is incorrectly relying on the model. Now that I've discovered these set of points, I need a way to communicate them to the human. And the way we're going to communicate them is by describing them in natural language. So now our problem becomes, we have a set of points and I need to describe it in natural language. I'm going to assume each point I can describe individually. That's not going to be a very hard task. And now my task is, how do I describe a set? A set that's embedded into a data set that contains other regions as well. So my algorithm is going to do the following. First, I'm going to randomly sample points from inside, so that's the set S plus, and points from outside, that's S minus. And intuitively, what you want is to contrast what's inside this region versus what's outside the region to understand its boundary and shape. So I'm going to take these two sets of points, I'm going to feed them to a large language model, and I'm going to ask it to contrast them. And I'm going to come up with an initial description that says, this region represents images that are highways during the night. Now, how can I improve on this description? What I'm going to do is I'm going to take this description I found. I'm going to embed it into my space. So I'm going to assume the space where I'm finding these points and is a cross-model embedding space, which contains images and text. So I can take this description, embed it into my space, and now find counterexamples to this point in my embedding space. And a counterexample would be a point that's very close in embedding distance to my description, but falls outside of the region. Another set of counterexamples is points that are inside the region, but have very high embedding distance. So that's the green point and red point, respectively. Once I find these counterexamples, I'm going to plug them into my sets, describe again. And so now I'm going to refine my description, and it's going to be highway during the night with no cars. And these two ingredients, first contrasting, and the second is the smart way to pick points, give us gains when we're describing regions. So one evaluation we performed, we took the MS Coco data set, which has images with captions, and there's objects that they contain almost 100 classes. And our job is to describe each class. So there's a set of images that contains apple. If you describe this set without the contrasting, you're going to come up with description fruit. If now you do a better job of finding out the boundary of this region, you're going to figure out that this region is fruit, is apple and not bananas. So that's going to be what this gain is going to do to you. And so here I'm showing the numbers, which is basically, did you get this exact region description captured by the Rouge metric? And with contrasting and with those counterexamples, you're doing a better job. So great. So now we have our regions, we have our descriptions. Now we need to convince the human that what we found actually makes sense, is actually correct. So we have each of these regions and described by roots. What we will do is, for each region, we're going to take a candidate, show it to the human, make them predict on this example, then show them the correctness of their prediction and show them more information about the region. And that's going to convince them through data that what we found as region descriptions, and they can edit them if they wish, actually makes sense. And so they're more likely to trust them in the future. And we're going to evaluate this procedure on exactly the task I made you play, which is, these blurry images and figuring out if there's traffic light or not. Also in our papers, we have tasks on question answering that evaluate this exact procedure. And so here you're going to try to answer if there's a traffic light or not, and you have the ask prediction and its confidence. So now to results. We can benchmark human performance without the AI, and it's at 78%. We can benchmark AI performance, and it's almost the same. We can benchmark the human AI team, so basically give the humans AI advice. We also train them on a bunch of examples, but not with our procedure. So we equalize their prior experience interacting with the model. And so they don't do much better than without the AI or the AI on its own. And with our procedure, we see an increase about 5% and significantly, statistically significant in this specific experiment. So that's great. So really the takeaway here is that you can train the person by creating these natural language rules that enable them to know when to trust or not trust the AI model. In other scenarios, the human's time might be constrained. So, if you think about healthcare, content moderation, the human cannot sit for each example and try to come up, and look at the AI's answer and try to come up. So we need a procedure that enables the human to not predict on each example and still create this human AI team that's outperforming either the human or the AI on itself. And the key insight to this is basically automating the human's mental model. So we've seen that we can create an optimal human that knows when to rely or not rely on the model. Why not just simulate that within AI, but on its own, and create that kind of team? And so this is the final part of my talk, which is going to be about training AI to do this kind of thing. So we're going to achieve this with something we call a deferral system. So we have our input X. Here we're going to assume it's a chest X-ray. We're going to build an AI model, which we're going to call the rejector, R of X. This rejector is going to decide on each input, whether to route it to the human or to the AI. So if this R of X is 1, a human, which is going to be a function of our X-ray and maybe some side information, which will compromise Z. So this human H of Z is going to make a prediction. If our rejector says 0, the AI, M of X, is going to make a prediction. So we're going to triage each example based on this rejector. And we're going to assume we have data of the following form. Tuples X, the input, the human's prediction, and a ground truth labeled Y. And so here we're assuming explicitly that the human is not perfect. So in this radiology example, the ground truth would be the consensus of 3 or 5 radiologists, while the single human prediction is 1 radiologist on their own trying to solve the case. And our goal is going to be to minimize the loss or misclassification error of the system. So here I'm writing out the probability that the final prediction is different from the ground truth labeled Y. So if R is 0, the classifier M of X is going to show up in this term. And if R is 1, the human prediction H of Z is going to show up. And now maybe the simplest way to build such a system is going to be as follows. You train your classifier as you usually do, ignoring that there's a human. You take the confidence of your classifier on this particular example X. You compare it to some threshold tau. And if it's below that threshold, you say that the human predict. So whenever the model has low confidence, you allow the human to predict. And the problem with this is that even if your model is not confident, it doesn't mean that the human might be better at this case. You have to consider the human's confidence. And that's work by Maitreya Raghu, who showed that you can do better by incorporating the human's confidence. The second point, which is shown by work by Eric and Brian Wilder, is that here your classifier is trained independently of the human. You could have trained a model that's better at the subset where you're using it at. So you train the model to complement where the human is bad, allow the rejector to assign the other set to the human and the set which we're good at for the AI. And so that's a better suggestion. And that's what we're going to do in our work. We're going to jointly learn this classifier and rejector pair to build a better system that's going to minimize the error. However, the fundamental problem we face is if you try to minimize this objective directly, even in the simplest setting. So if you're trying to learn a linear model and linear rejector, and even if the data is reliable, so that there exists a team, a classifier rejector pair that achieves 0 error, this is computationally hard. And so you cannot just straightforwardly minimize this objective. And so we're going to follow the standard recipe in machine learning, which is going to be to build a surrogate that's easily differentiable through gradient descent, and we can optimize to obtain our classifier rejector pair. And the way we're going to do this is by writing out the log likelihood of the human AI team. So here I'm applying Jensen's inequality and showing you the result. If you took our error from before and allow our classifier and rejector to be probabilistic. So on each point, there's a likelihood of deferring or not deferring to the human. And the classifier is going to make a probabilistic prediction according to a specific parameterization which we're going to show. So our loss is really very intuitive to see. The log of the probability of the classifier getting it right times the probability of not deferring plus the probability that the human is correct times the probability of deferring. And the specific way we're going to parameterize the classifier and rejector is going to be as follows. We're going to define a set of scoring functions. So G1 up to GC, where C is the size of our label class. So if we're predicting healthy or not healthy, C is equal to 2. So we have a function for predicting healthy and function for predicting unhealthy. And then we're going to define an extra scoring function, gbot, which we're going to use for our rejector. So the probability that the classifier m of x predicts class 1 is really going to be the score of the scoring function gy normalized with the softmax. And then the probability of deferring is going to be the score of the gbot, again normalized by the softmax. And their normalization is going to share all of these scoring functions as a way to link the classifier and rejector parameterization. And what we can show is that, and so if you plug in this parameterization into our log likelihood, you get something that resembles the cross-entropy loss a lot, but instead of in this numerator, you have these two terms which correspond to either classifying or predicting or deferring. And you only want to defer if the human is correct. And so now you have this realizable surrogate. What can you say about it? And so what we can prove is that in the case where there exists a human AI team with 0 error, in fact, minimizing the surrogate will provably find it. We're not making any claim about computation, but the fact that we can minimize the surrogate through gradient descent and through a bunch of experiments, we can show that it will find this 0 error human AI team. So we can find a way to circumvent this hardness through this optimization. And really, the recipe is very simple. Before, if you were doing standard machine learning, you would have your neural network, which has these scoring functions. You will train with cross entropy. If you want a model that accounts for the human and can defer, what you do is just add one output to your neural network, swap out cross entropy loss, put the realizable surrogate, and now you have a model that's capable of deferring or predicting while incorporating the human. And so we have a bunch of experimental evaluations on our paper. I'm just going to highlight one of these for sets X-ray. So again, we're going to do the same thing, benchmarking radiologist performance, AI performance here was going to be a bit less, and then the baselines we've considered. So thresholding just on model confidence, which is really not going to improve on the radiologist on its own. With this procedure by Arago, which incorporates the comparison between human and AI confidence, and finally our method, which is going to train the classifier additionally. And we can achieve kind of this different performance from the radiologist or the AI by only using the radiologist 50% of the time. And again, we have a bunch of more experimental evaluation to understand the performance process. And so really here, the takeaway is that by incorporating the human into your optimization objective, you can achieve performance that's even higher. And finally, I want to just talk about what's coming next. What's the future of these human AI teams? And really one of the open questions is, how do we interact with models that rather than just give us advice, can perform actions on our behalf? So that's a new challenge which we haven't considered in this thesis. The second question is, in these settings when we're writing or working in our systems, how can we have the AI proactively know when to assist us and when not to? The final challenge is, as humans are interacting and making decisions with AI models, how will human skill evolve over time? Will we see a descaling in our performance, or will we see different trends that will emerge?